Something we've been exploring in class has been proving things mathematically, and we can do a range of different styles of proof dependent on the problem that we've got in front of us. One thing that I really wanted to make clear is the difference between, proving something mathematically and, in inverted commas, proof in science. And you'll know why I say in inverted commas, proof in science, in just a moment. So, in science, hypotheses can actually never be proved. They can be supported, but never proved. So when you see on the television it says scientists have proved that eating 12 carrots a day will extend your life by 50 years, they haven't actually proved it. They may have research that perhaps supports a hypothesis, even though that seems like a very outrageous claim, but they cannot prove something. They can only support. In maths, it's actually quite different. We can rigorously prove things we're going to use 3 methods in Specialist this year, but there are other methods that you can also use. So this lesson is going to be about direct proof, and there will also be separate videos on proof by contradiction and proof by induction. So basically, when you start with a proof, you're starting with a mathematical statement that has not yet been proved. Now, it may have been proved by people in the past, but what I mean is something that's not been proved by you. And I also want to note there's sometimes more than one way to do these proofs. The proof for Pythagoras' theorem we'll be exploring in a future topic. There's a whole bunch of ways that you can prove that. There's so many, and it's really interesting, and they're all tackled at different, with different approaches. Direct proofs are possibly the easier kind of proof to start off with. So the recipe is sort of as follows. You're going to basically write a clear conjecture, so that's something you're trying to prove using appropriate mathematical notation and terminology. Then you're going to show that the left-hand side, and you're probably going to have an equation, can logically be used to produce the right-hand side, which we're going to use RHS and LHS for those shortenings. I sometimes call this the do stuff step. And the reason is we're often just performing basic algebraic manipulations or, finding common denominators or things like that. So when I say do stuff, it really depends on the context of what you've got. But I'll show you with some examples. Once proved, something that people tend to do at the end of the proof is they'll put a little box. That's like the full stop at the end of the proof saying, here we go, I finished the proof, you're welcome. Some people like to write QED instead. I am told that that is the more snobby way of doing it. But, if you want to do that, I really don't mind. Now, one thing you can't do is start off by writing right-hand side equals left-hand side and then doing manipulations to that equation, because you're assuming that equality is true. We cannot assume that equality is true. We're going to instead start with the left-hand side, show that the right-hand side follows, and then therefore say, okay, well that means left-hand side has got to be equal to right-hand side. You cannot start with this. You end with this. I'll show you what we mean. Okay, we're going to start with an example. We want to prove that the sum of 2 odd numbers will always be even, but the product of 2 odd numbers will always be odd. In effect, we have 2 proofs we're going to do here, so let's just put a line because there's 2 proofs. The first proof is going to be the sum of 2 odd numbers will always be even. The second proof will be the product of 2 odd numbers will always be odd. So we'll call that 1 and 2. Proof 1 and proof 2. Ooh, that 2 went a bit funny. Okay, proof 1. Now, in order to do this proof, we need to be able to write a generic odd number. In order to do that, we can't just say, we're just going to say n, and n is an odd number. We can't just write that next to it. We need to be able to make it a generic odd number that works for any value of n, because we're going to be saying n is an element, of the natural numbers for now. You will see that it can be an element of the integers, but we're just going to stick with the positive natural numbers for now, just to make our lives a little bit easier. So if n is a natural number, n can take the value of 1, 2, 3, 4, 5 going on forever. But the problem is we only want n, we only want our numbers to be odd. So some people suggested in class, well, we could write 2n. Now, that would be handy because if we subbed in n equals 1, we'd get 2. Sub in n equals 2, we'd get 4. Going on and on, that would always give us an even number. But we want to specify that we always want an odd number. So one way we could do that is putting in 2n plus 1. And in fact, now that I think about it, let's indeed make this the integers, because then we can sub in something like n equals 0, and we'd get 1. So we're getting any odd number here. We could also get negative odd numbers. So that will give us an odd number. We also want to write a second, oops, it's gone to Google. We also want to write a second odd number, and a lot of people had ideas for how to do this in class. Some people suggested we did 2n plus 3, because that would give us an odd number. But the problem is, that would be, the next consecutive odd number. Consecutive means the next direct number. So if we had, n equals 1 in here, we'd have our first odd number would be 3, and if we had 2n plus 3, the next odd number would be 5. That's the next consecutive odd number. But we want 2 odd numbers. They don't have to be consecutive, just any odd numbers. So a suggestion made in class is that we could say, okay, let's do 2m for Mary plus 1, and m is also an integer. So if we do that, we've just got 2 random odd numbers here. Now, so this is really important, and something you might want to make a note of, on the side of your page or at the top of the page or something. I'm going to make it on the side. If we have 2n plus 1, where n is an element of our integers, that's a generic odd number. If we, like we discussed before, had 2n, where n was an element of the integers, that would be an even number, because 2 times something is going to be even. And don't ask, do we have to prove that 2 times something is even? That's the definition of even, being a multiple of 2. So we're allowed to assume that. So I've talked about that for a reason, because we're about to get into proof number 1. We've sort of set up a few things. We set up our 2 odd numbers, but we need to actually do the proof now. It says the sum of 2 odd numbers will be even. So we need to do the sum of our 2 odd numbers. So we've got 2n plus 1. Let's do the sum of those, plus 2m for Mary plus 1. Okay, so if we put them together, we're going to have 2n plus 2m plus 2. Now, you may not realize it, but we're one step away from our proof, like being completed. If we look at what we've got here, we have a common factor of 2. So this is the do stuff step I was talking about. We set up our proof, we had 2 odd numbers, and we're just doing things that algebraically make sense. So from this line to this line, all we did was put the 2 ones together. And now we're looking at what we've got and saying, hey, we've got a common factor of 2. Let's take that out. So n plus m plus 1. We said in our generic definition of an even number, 2 times a number would be even. Well, in this case here, in the bracket, it's just a number. It's a random number n, which could be any of our integers, plus a random number m, which is also any one of our integers plus 1. It doesn't matter what the individual value of n and m are. All that matters is that we've got 2 times an integer. And 2 times an integer we defined as being even. So, in effect, we've finished our proof. So we need to make some sort of statement to say we've done what we were actually looking for. So you can say, this is even. And then I'm a bit flexible about how you sort of conclude your proof. You could say this is even as required, or something like that. Or you could even restate, so therefore 2 odd numbers added together give an even. I'm going to cheat and just say as required. And we're going to put a little box. So in this example, we started with the sum of 2 odd numbers. We didn't assume they were even. We started with the sum of 2 odd numbers. We did stuff, and by did stuff, we did common algebraic manipulations, and we ended up with the conclusion that it had to be even. We didn't start by assuming that. We started with our proof, started with the sum of 2 odd numbers portion of our proof. We did common algebraic manipulations, and then we ended up with an answer that always had to be positive. If you feel you've really understood that portion of the example, I want you to have a go at number 2. If you want, you can pause the video. If you're still not feeling super confident, you can just watch along with me. We're going to use the same 2 odd numbers that we had before because we've already organised them, 2n plus 1, 2m for Mary plus 1. But instead now we're going to do the product. So let's set up that product. So we're going to have 2n plus 1 product of 2m plus 1. And hopefully you can see a reasonable algebraic step at this point. Might possibly be just expanding the brackets, because that's what you do when you have, 2 terms inside of 2 brackets multiplied like this. 2 terms in each bracket. I hope that made sense. So if we FOIL this, we're going to have 4nm plus 2n plus 2m plus 1, because 1 times 1 at the end. And just keep in the back of our minds, we're trying to show the product with 2 odd numbers will always be odd. So don't forget about our generic odd number. If we had 2 times a number plus 1, that meant the whole number had to be odd. If we look at what we've got here, I can see that the first 3 terms are even. So, keeping in mind of what we look for when we've got an odd number, let's take 2 out as a common factor, but just of those first 3 terms. So if we take it out here, we'll have 2nm plus n plus m, and we've still got plus 1 on the end. So we've effectively manufactured an odd number again. We have 2 times something, doesn't matter what this something is, 2nm plus n plus m. Doesn't matter what the individual values of n and m are. We know they're integers, and we know an integer, the product of 2nm and then plus n plus m, that's just going to be an integer times 2, which will be even, plus 1 makes it odd. So therefore, the product is odd. You could say as required, but it says the product of 2 odd numbers is odd in the proof, so I'd be happy with you just doing a box here. If you didn't have this from the previous question, I need to make it clear, you would need to include that at the start, but because it was part, 2 things that were related to the same thing, you're allowed to do that there. So that's why this one looks a bit shorter than the one we had before. Okay, so in the next example that we've got, the short proof, we want to prove that for all n and m are elements of our integers, that's what z is, n plus n squared equals 2m. There's actually a bunch of ways that you can show this example works. Here's just one way. So if we start with this, we cannot start by writing n plus n squared equals 2m. You can't assume that. And all this is saying is prove that n plus its square gives an even number. It's just saying prove that this is even. It doesn't matter what m is itself. So it's a little bit strange to look at it like that, but a lot of what we do in proofs, especially when you're just learning about proofs for the first time, is using even and odd, even positive and negative in our rationale. It's just a different way of thinking about maths. So one way you can do this proof is starting with what we need to prove. So n plus n squared. We're not writing equals 2m because we're showing that it's going to be even. The shortest way of doing this proof is, well, let's look at what we've got. N plus n squared. We could take out a common factor. So we could take out a common factor of n. And then we'd have 1 plus n in the brackets. Hopefully you can see that's exactly the same as n plus 1. Now, this is interesting. We've got n, and we've got n plus 1. N is an integer, and n plus 1 would be the next consecutive integer. So I'm just going to do a little thinking thing here. So n plus 1 is the next integer after n. So that means we've got a number and the next consecutive number. An example of this, 17, 18. I know, random numbers, I don't know why I chose them either. But the important thing about 2 consecutive integers is one is odd and one is even. That's always the case. That's how even and odd works. If one is odd, the other one must be even. And so I'm going to write, one will be odd, one will be even. One odd, one even, because consecutive numbers. Now, we're really hoping that the product of an odd and an even is going to be even. So we need to do a side proof. So, side proof. I want you to have a go at proving that an odd number times an even number is an even number. If you need to pause the video and have a go, that's fine. If you want a hint, you can pause after the hint. So, hint. Let's make two numbers. We're going to make an odd and an even. Let's not use the letters N and M because we've already used those within our initial statement. So let's use A and B. And we'll use A and B, which I'm just going to put over here. A and B are both going to be an element of our integers. We're going to use those to construct an even and an odd number. So let's have 2A and 2B plus 1. And like we talked about before, we would have 2A would be our even number. So if you want to put a little note, that's even. And 2B plus 1 would be our odd. And we need to show that the product of this will be even. So let's do 2A times 2B plus 1. There's multiple ways you could do this. You could expand everything out and then take out a common factor of 2. Or you can just say, well, there's a factor of 2 out the front. Or you could be kind of tricky and distribute the A through here, and you could say, well, 2 and then 2AB plus A, because there's that common factor by itself, you can say it's even. So we can now say, because an even times an odd is an even, then n squared, sorry, it was n plus n squared, you could have written n squared plus n, is therefore even. And we finished our proof, so do a box. Oh, in our mini proof we finished too, so let's do a box there. Occasionally you need to do a side proof to prove something. And some people in the class got a little bit concerned, oh, how often do I need to do a side proof? What kind of things am I allowed to assume? Anything that you've done within the notes, you're safe to assume. Oh, 1 second, my dog is barking. Okay, I can't really remember what I was talking about before. Oh yeah, we were talking about relying on previous proofs. So what we're doing now is a bit of an interesting side topic that we do within Year 11 maths, Year 11 specialist maths. Don't get too wrapped up about worrying about previous proofs and doing side proofs and that kind of thing. The questions I set you in a test scenario are ones that you will be able to manage. If I set you one that was much more involved and relied upon a whole bunch of previous proofs, that would be something that I would give you in an assignment. So something that you could do at home. Hello, my little barky dog just came in. Hello. Hello. You're going to be quiet? Good girl. Okay, so let's have a look at this proof. We want to prove that if a number is odd, its square is also odd. And we want to show the same proof for even numbers. So pretty similar to before, we're going to have two separate proofs here. We're going to have one for if a number is odd, its square is odd. And then we're going to have one which is going to be the same proof but for even numbers. Let's start off with a generic odd number. So you can pick whatever letter you like. I'm going to choose P for this example. And P is going to be an element of our integers. And we're starting off with the number as odd. So let's have 2P plus 1 to be our generic odd number. We need to show that its square is also odd. So hopefully you're like, well, let's square 2P plus 1. Please remember that is not just equal to 4P squared plus 1. That is equivalent to, and if you need to do this in between step, that's fine, this. But many of you can probably just do it in your head from this step, 4P squared plus 4P plus 1. How you do the finishing steps of this proof is really up to you. I'm going to show one option, so I'm going to write option 1. You could take out 4 as a common factor from the first two terms. You'd have P squared plus P. You don't need to worry about taking the P squared. We're just trying to show even and oddness here. 4 times a number, well, 4 is 2 times 2. So 4 has, the factor, a repeated factor of 2. So 4 times a number has to also be even. So that's an even. And if we add 1 to that, that's an odd. So that could finish our proof. So if you like that, you can write that one down. And you can pause it because I'm about to erase it. Some people didn't want to be that flexible. They really wanted to get it into the form of 2 times something plus 1. So if you wanted, option 2, you could write that as 2 and then 2p squared plus 2p plus 1. And that's very clearly, an even number plus an odd number. So they could say, therefore, odd, and then they finish their proof. And you might even have another way that also works. I am very comfortable with what you do so long as you're explaining your steps. And you're allowed to assume that your examiner knows that 2 times something, your integer here, plus 1 is odd, but you still need to say it. Because you've got to say, I also recognize this. And then you've got your square to complete your proof. I want you to have a go at the next example and see if you get the same thing, and the solution will be up in just a moment. So I think the even proof is a little bit easier. We've just got 2q squared, which is 4q squared. And remember, even means it is a multiple of 2, and 4 is 2 times 2, so it's definitely even. Okay, I'd like you to have a go at the next example. So I'm just going to put a star here. The 2, is it 2 or 3? The 2 examples after that are a little bit trickier, but this is one that you'll probably be able to do too. And part of your homework is going to be looking at this example here. It's in your textbook if you get stuck, but you can definitely look there. So let's have a go at one of the last of the simpler direct proofs. And as I said, this one here is challenging and the one after it is too. I would like you to actually have a go at this one by yourself. So I'm going to pause and write the solution and talk you through it, just because this video is starting to get quite long. So how'd you go in this proof? I realized I've made a mistake as I've started filming this. You notice I've written a equals 2a and b equals 5b. It doesn't make sense. So I actually need to change these values, a and b, to something else. And you might be like, why can't I just write 2a and 5b? Well, a needs to equal an even number. So we need to express that in terms of something else. So I'm going to use the good old p and q. You could use x and y. So I'll change it to p and q, p, q. So that's something that people tend to make a mistake, and when I was like, oh, I need to pick 2 random letters, I'll pick A and B, I forgot they were already used within the question. So we can express A, an even number, as 2p. Even just means that it is a multiple of 2. B equals 5q, because we said it was a multiple of 5. Multiplying them together gives 10pq, which is divisible by 10. That's a nice proof. The next one's not as nice, so I'm sorry in advance. Let x and y be positive real numbers. So x, if it's a positive real number, x is going to be greater than 0 and y is going to be greater than 0. We want to prove that if x is greater than y, then x squared is greater than y squared. So we're going to start with this. We're going to get to this. So we can't say this, therefore this is true. We need to show that this is true. But we've also given this information. X is greater than 0 and y is greater than 0. So that's kind of handy. So I'm giving you a tip. This one's harder. Not as straightforward as our previous proofs. So let's write down the last bit of information that I said we know. We know that x is greater than y. Sometimes it's useful having it all just written in a line. If x is greater than y, that means x minus y has got to be greater than 0. It's like we started with this and we took y away from both sides. But if x is a bigger number than y, a big number take away a smaller number has got to be greater than 0, because we said both of those numbers were positive. Here's the tricky bit. You may not like this. X plus y has also got to be greater than 0. You might be like, how on earth did you know to do that? I'm going to show you how in a little bit, but I just want you to understand, why does that step work? Hopefully you're like, of course it does. X is a number bigger than 0. Y is a number bigger than 0. So if I do the sum of x and y, that's also going to be bigger than 0. Another thing, and I know where we're headed, so this is how I know the magic of what's going to come. If we do x plus y times x minus y, that's also going to be greater than 0. This is a positive, and this is a positive, so its product must be positive. Now we're going to learn in a future lesson that how to prove, that a positive times a positive is indeed a positive. So if you're worried about that, don't worry, that proof is coming. But for now, let's just rest upon that we know a positive times a positive is indeed positive, and positive means greater than 0. The reason why that's so handy, and the reason why I thought to do that, and people who've proved this previously have thought to do that, is because when we expand this out, this is going to be very difference of perfect squaresy, DOPS. Because when we multiply this out, we're going to get x squared minus xy plus xy minus y squared, which simplifies down to just x squared minus y squared is greater than 0. And hopefully that's very exciting to you, because you're like, oh, we could just add y squared to both sides, and we've proved what we were trying to show. We prove that if we start off with these conditions and we follow mathematical conventions, this one required a little bit of a trick and a little bit of a trick here, but logically it followed if we had two positive numbers, x and y, if x was greater than y, then x squared had to be greater than y squared. And I'm happy for you to just put a box there because you've shown exactly what we had to show here. So I knew the trick for that one, and I also know the trick for the next one, which you may not like at all. But let's have a go. This is going to be a speed round because I realise I am meant to be in an appointment in 5 minutes. Luckily it's a 3-minute drive, but I need 1 minute to get ready, so let's see if I can do it in a minute. I don't think I can. Okay, speed round. So we've got two integers. We've got n and m. New thing, it says n is greater than m, and we want to show that that means 1 on m is greater than 1 on n. I thought I was recording and I wasn't. I'm running late for something, so I need to do this one very quickly. We want to prove that for two integers n and m, we want to show if n is greater than m, then that means that 1 on m is greater than 1 on n. To visualize this question, sometimes it can be useful looking at it in terms of actual numbers. So if we had 3 and 2, for example, 3 is bigger than 2, and a half is greater than a third. So that's nice to sort of visualize the question. Now, this is another one where there's a trick that needs to be performed, and the trick really is this step, although the trick sort of is in another step too. So if we start with n is greater than m, we can take m away from both sides to get our second line here. And then, mathematically, we can divide both sides by n on m. As I was talking about when I wasn't recording, 0 divided by n on m. We can divide both sides by the product nm. 0 divided by anything is just 0, so we can just leave 0 on that side. The reason this is useful is we can now break this up into two fractions. We could do n on nm minus m on nm is greater than 0. Keeping in mind, we've always got where we're eventually going in our thoughts. That's our thought bubble for when we're doing things. This is going to be helpful because on the first fraction we can cancel off the n's, and the second we can cancel off the m's. So 1 on m minus 1 on n is greater than 0. And hopefully you're like, oh, awesome, 1 on m, let's add that 1 on n, is going to be this. So that one's a little trickier, but keeping in mind that's what we wanted to end up with, hopefully you realise we needed to introduce a fraction, and dividing by nm in this step was, something providing a fraction there. And the reason we chose nm is so we could go to this next step and cancel off the n's on the first fraction and the m's on the second. Okay, I really cannot continue this video any longer than it is. I want you to have a go at this. It says, prove that for all integers n squared plus n plus 1 will be an odd number. I want you to have a go at trying this for odd and trying this for even. And then there's an even shorter proof. We previously showed that n plus n squared was even, so you can use that. And you can have a look in the OneNote to see the completed notes. The last bit, that is going to be something that you look at from your text, and you're now able to try the selected questions from 8A, which you don't need to worry about wondering about which ones they are, because they're listed in this book. Yes, I could have written questions 1 to 11. I think I wanted you to be able to cross it off as you went, but you may not like to do that. Okay, thanks. Bye-bye.